Hello everyone, and welcome to the 7th chapter of our Chemistry O-Level Lessons series. This chapter is called Chemical Formulae and Equations. So without further ado, let's begin. So here we are on Chemical Formulae and Equations. Here we have some of the learning objectives of this chapter, and you can find the specific topics of this chapter in the description below along with their timings. So in this chapter, we should be able to state the chemical symbols of the common elements, deduce the formulae of simple compounds from the relative numbers of atoms present and vice versa, define the relative molecular mass of a compound, and learn to calculate the relative molecular mass of a compound given the relative atomic masses of its elements. We're going to calculate the empirical and molecular formulae from relevant data, construct balanced chemical equations with state symbols, construct ionic equations with state symbols, and interpret chemical equations with state symbols. So, in short, this chapter is going to be about chemical formulae, equations, how we can construct equations, what are the rules of constructing equations and balancing equations, and how we can interpret chemical equations, and how we can find the relative molecular mass and atomic masses of elements from compounds or any other stuff. So let's start this chapter by first looking at the chemical symbols of some of the common elements from the periodic table. So here is this chart of some of the common elements from the periodic table along with their symbols. In this section we have a first letter only. Like in these elements, their symbols are the first letter of their names. Like boron's first letter is B, so its symbol is B, capital B. It's always capital, the first letter is always capital. Carbon is C, hydrogen is H, iodine is I, nitrogen is N, oxygen is O, sulfur is S, uranium is U, and phosphorus is P. Then we have the elements with the first two letters as their symbols. Like we have a name like aluminium, and the first two letters of this name would be the symbol of this. So aluminium is Al, bromine is Br, cobalt is Co, helium is He, neon is Ne, argon is Ar, nickel is Ni, barium is Ba. All the first two letters, Ba, Ni, argon is Ar, as you can see. But then we have the elements with the first and third letters. So in this we have the first and third letters, not the second one. Like chlorine, we don't write CH in chlorine, we write Cl. So it's the first and third letter from the name, Cl. In magnesium as well, Mg. Manganese, it's Mn. Zinc, Zn. Chromium, Cr. So the first and third letters. And then we have some of the elements whose symbols are from their Latin name. Like copper, copper's symbol is not Co, Cp, or even C. It is Cu. And Cu might relate with copper, but it's actually coming from its Latin name, which is cuprum. Cuprum is written like this, and so the first letters of cuprum is C and U. So copper's symbol is Cu. Then we have gold, whose symbol is Au. It is absolutely different from its actual name gold, but because it comes from its Latin name, which is aurum. And the first letters of aurum is A and U, so that is why symbol of gold is Au. Then we have iron, which has a symbol Fe. I mean, we're quite used to these symbols, but usually the symbols are related to the element's name as well. So when we're in the beginning trying to learn the periodic table and the names of the elements along with their symbols, it might be a little difficult for you to remember. You might say Co is for copper, even though Co is for cobalt, or C is for copper, even though C itself is for carbon. So for copper it is Cu. It is not related to copper as we have no U in the copper, but you should remember that it comes from the Latin name cuprum. Gold symbol comes from its Latin name aurum. Iron is ferrum, so that is why we write Fe. Lead is plumbum, so we write Pl for lead. Completely different from lead, but it comes from the Latin name plumbum, Pl for lead. And for mercury we have this, hydrogyrum. I might be pronouncing it incorrect, maybe, but it is something like this. It's a Latin name. And you might get a little confused in this because usually all the Latin names we have read so far, the symbols are of the first two letters of the Latin name. Like cuprum, the first two letters of cuprum is Cu, so that is a symbol. Same for aurum, ferrum, and plumbum. But in mercury, we have Hg rather than Hy. You know, the Latin name starts with H and Y, but the symbol is not. But the symbol is not Hy. It is Hg, and G is the fifth letter. No, actually, it's the sixth letter, G. So just remember that Hg is the mercury's symbol. Then we have potassium. For this, we have K, capital K. Only K, no two letters, only one letter. And this comes from its Latin name, kalium. For silver, we have argentum. Argentum or argentum. It's just, please do not rely on my pronunciation. In this, we have the first and third letters of the Latin name, Ag, not Ar, Ag. For sodium, we have natrium. It's probably going to be natrium, but I'm still not sure about these Latin names. And sodium is Na. First two letters. Tin, for tin we write Sn, which comes from stannum. Again, it's not the first two or even the first and third letters. It is the first and fourth letter. Sn is for the tin. So these are all the elements whose symbols comes from their Latin names. These are the elements whose symbol come from the elements' first and third letters. Here we have the first and two letter symbols, and here we have the first letter only symbols. These ones are the easiest. So this was the entire table of the chemical symbols, where these chemical symbols are derived from for each of these elements. I would recommend you to memorize this entire table so that it becomes easier for you to understand which symbol represents which element. So that whenever we see a symbol, because usually we don't write the entire thing like boron, carbon. We usually write, like in chemical equations as well, we write the element symbol. And so if you remember the element symbol, you would be able to recognize what element we're talking about through the symbols. So if it is written CO in a chemical equation, reacting with some other element, we won't write their entire name like cobalt and iodine or something like that. We would use its symbols for chemical equations. So that is why it is important to memorize all the symbols for all the different elements. And it's pretty simple. The more you read the chapter with me, the more you read book, you're just gonna get used to these symbols yourself automatically. And don't take these Latin name symbols too seriously. It's gonna be easy to memorize as well. The more you read, the more you come across them, they're gonna just get memorized themselves. But still, it is advisable to memorize this entire table right now. So these were the chemical symbols. Now we're going to look at chemical formulae. So every chemical compound is represented by a chemical formula, which is an expression of the ratio of combining numbers of atoms or ions. Okay, so we've read about this in this previous chapter and the second last chapter we did. I mean to say the 6th chapter and the 5th chapter. We read about this stuff in those chapters, chemical compounds and their formula. So how chemical compounds are formed. Two different elements react to form a compound. And this compound is made up of these two elements in different ratios of combining numbers of atoms or ions. And this compound is represented by a chemical formula, which is an expression of the ratio of combining numbers of atoms or ions. Okay, so in the previous chapter we learned how atoms bond together to form these chemical compounds, covalent and ionic compounds, the different types of bonding and stuff. And in this chapter we're going to look at the chemical formulas which are used to represent these chemical compounds and how they are formed. So these may be determined experimentally or by using a list of ions. The charge on an ion is a measure of its combining power or valency. So atoms are ions. These ions bond together to form compounds which are neutral in the end. Like we read in the previous chapter, ions are obviously not stable. They have some sort of combining power or valency. They have a charge on them, either positive or negative. And then the positive and negative ions merge together, they cancel each other's charges out and become neutral and form these compounds or molecules. Covalent bonding makes molecules and ionic bonding makes ionic compounds. So, remember, the charge on an ion is a measure of its combining power, or valency. Valency comes from valence electrons. If you remember, in the previous chapter we read that the valence electrons play the main part in bonding, because valence electrons are the reason why atoms become unstable and bond with other atoms to reach stability, because every atom wants its outermost shell to be complete, and these valence electrons cause them to not be complete, and that is why they react with other atoms to lose these valence electrons or gain some more electrons to add up into their outermost shell to make a complete octet. So the charge on an ion is a measure of its valency. We see we write a symbol and we write a plus symbol as well with them, or a +2 symbol, and that is basically the charge on this ion. It is basically the valency. That symbol +2 or plus or +3 is the valency, or -2 or -3. That is the combining power, or valency. Okay, I hope you've understood this. So when an ionic compound is formed, it involves the transfer of electrons, resulting in the formation of positive and negative ions. So the number of positive and negative ions involved is such that the number of positive charges equals the number of negative charges. Okay, yeah, I forgot to tell this, that these charges form whenever the transfer of electrons occurs. Before that, they are not charged. They're just unstable. They want to give their electrons to someone and the other one wants to gain some electrons. So when they do this, when an atom gains an electron, it becomes negatively charged because negative particles entered its atom, so it will become negatively charged, and the other atom which loses the electrons becomes positively charged. And so these charges basically form these ions. They become ions, The atom which is gaining the electrons becomes a negative ion, and the one that is losing the electrons becomes a positive ion. But the number of positive and negative ions involved is such that the number of positive charges equals the number of negative charges. So the negative charge, for example, the atom gained the electrons and it gained a single negative charge. Then the atom which lost the electrons would gain a single positive charge. Remember, these charges would be equal. And so when the charges are equal, they cancel each other out. In the end, we have a compound which is neutral. It is not an ion. It is not charged. So consider the compound sodium chloride. Here the sodium ion, as you can see, we have written the symbol. The charge is +1. So we do not write +1, we just write plus, which represents 1, a single charge. So here the sodium ion has a single positive charge because it's a plus sign, and the chloride ion has a single negative charge. It's a minus sign. So its chemical formula is NaCl. They cancel each other out. Single, they cancel each other out. The same is if the charges are 2. So if this atom has +2 charge and the chloride ion also has a -2 charge, they would again cancel each other out. And in the end we would have NaCl, because the charges just cancel each other out. We're not going to write 2 here. They're just going to end. They're going to disappear because they're canceling each other out. But if we have an atom whose charge is more than this atom, like for example, this atom has a charge of -2 and this atom has a charge of +1, then they're not equal. We would need to have 2 of such atoms to bond with this atom, so that 2 single charges would bond with 2 minus charges, and then they would be equal. And then again the charges would cancel each other out, but the number of atoms would be different. This time it will be Na2Cl, because we have 2 sodium atoms and only 1 chlorine atom. So then the number of atoms would change, but again charges would cancel each other out. So whenever a compound is being formed, the charges cancel each other out. There is never any charge on the end product, on the end compound. And this charge thing only happens in ionic bonding, not in covalent bonding. Because in covalent bonding, electrons are being shared, not transferred. And so that is why no ions are formed. I hope you remember the previous chapter well. So these are the charges. And these charges on each of the ions is the ion's valency. So this charge on an ion is a measure of its combining power, which is valency. Basically, these charges represent the valence electrons. That is why it's called valency. If the sodium ion has a single positive charge, then we will say that it has 1 extra electron. If it was a double positive charge, like a +2 charge, then we would say that it has 2 extra electrons in its outermost shell. And so that is why we call these charges the valency of this ion. Same is for the chloride ion. If an atom has minus written with it, then this atom is short of 1 electron for a complete octet. It needs 1 electron to complete its octet. And if it's -2, then it needs 2 electrons to complete an octet. Usually it remains in 2 or 1, and it never comes to 3, because gaining or losing electrons more than 2 is not possible. Even though aluminium is an exception, that it has a charge of +3, but still it's not usually possible because it requires too much energy. So the chemical formula of sodium ion and chloride ion is NaCl. However, in the compound sodium carbonate, we have sodium ions, Na with a single positive charge, and carbonate ions, CO3. So as you can see, the charge on this carbonate ion is 2 minus, not -2 actually, is written a little differently. 2 minus, not -2. So when we say 2 minus, it means that it has a double negative charge, like 2 negative charges, whereas sodium has only 1 positive charge. So in order to balance the number of positive and negative charges, it is necessary to have 2 sodium ions to every 1 carbonate ion. Like I said in the previous, that if this atom has a single positive charge, but this atom has a double negative charge, like 2 negative charges, then we would need to have 2 of these atoms to balance out the charges. This is what is written over here, that it would be necessary to have 2 sodium ions to every 1 carbonate ion. And so the chemical formula of sodium carbonate is therefore Na2CO3. The charges get cancelled. So that is why we don't write them, because they're cancelled before we write the charges as well. And so we write Ca2CO3 because 2 represents the number of atoms. And CO3 itself is an entire molecule. So 3 does not represent CO. 3 is the number of oxygen in carbonate ions. 1 carbon atom and 3 oxygen atoms makes the carbonate ion, and 1 carbonate ion is with 2 sodium ions, and that is why sodium carbonate is formed. So here we have sodium, which has a single positive charge, carbonate, which has a double negative charge. They both bond together to form Na2CO3. We use 2 sodium ions and only 1 carbonate ions, and so using 2 sodium ions we got the total charge of +2, and using only 1 carbonate ion we get a charge of -2, and so they cancel each other out, so the end product has no charge. So then we have something a little different, aluminium. As I said, aluminium is an exception for what I was saying, that usually the loss or gain of electrons is between 1 or 2 electrons. It never reaches more than that. No atom gains more than 2 electrons or loses more than 2 electrons, but aluminium is an exception. This has a charge of +3, +3. So it needs to lose these 3 extra electrons in this outermost shell, because gaining more than that is not possible, of course. Usually in these cases, covalent bonding occurs, but aluminium here is an exception. Ionic bonding occurs in aluminium. So to lose these 3 electrons, it needs an atom which also needs 3 electrons. But rather than finding a single atom which needs 3 electrons, we find an ion which needs only 1 electron, which is nitrate in this case. Nitrate ion has only a single negative charge. So we use 3 of these nitrate ions, and because the aluminium ion has a positive charge of 3, 3 nitrate ions would have a negative charge of 3. And so they would bond to form aluminium nitrate. The charges cancel each other out, and the end product has no charge. So we write it like this, because we need a 3 that represents the number of this single ion. So because there are 2 3's coming, 1 3 is because of the ion. The ion is NO3, nitrate. Nitrate is made up of 1 nitrogen atom and 3 oxygen atoms. So to separate the other 3, the number of atoms 3 with the number of oxygen in nitrate 3, we just bracket this nitrate out, so that it becomes easier to understand that we have only 1 atom of aluminium and 3 atoms of nitrate. The brackets are used to show that it needs 3 complete nitrates. Okay, I hope you understand. Here we have a chart of the valency of some ions. Here we have the positively charged ions, and here we have the negatively charged ions. I would really recommend you I really want you actually to memorize this entire table, as it will be so helpful in the upcoming things we're going to learn. Very helpful in making chemical equations. So here we have the positively charged ions and the negatively charged ions with a valency of 1. One positive charge and one negative charge. For positively charged ions, we have sodium, potassium, silver, copper, hydrogen, and ammonium. Ammonium is a compound, as you can see, CH4. Sodium, potassium, silver, copper, hydrogen. These all are positively charged ions with a valency of only 1, like one positive charge. Then we have the positive charged ions which have a valency of 2. Two positive charges, which are lead, copper, magnesium, calcium, zinc, barium, iron, and mercury. They all have 2 positive charges. Then we have the ions with 3 positive charges. These are very less, really rare. Iron and aluminium. Now, as you can see, some of the elements here have 2 different charges. Like iron has a valency of 3 as well as of 2. So it is in the form of 2 different ions. And to differentiate between these 2 ions, we write numbers in Roman, like 2 and 3. We're going to see this a little later. But right now, here we have the positively charged ion with a valency of 3. 3 positive charges. Iron and aluminium. We write their charges like this. Single charges are written as only the symbol, plus. We write minus for negatively charged ions, and plus for positively charged ions. If it is only one valency, then we don't write 1 with it. Then we have 2. If the valency is of 2, then we write 2 plus, not plus 2, okay? I know I have been saying this a little incorrect. We write 2 plus. And if it's a valency of 3, then we write 3 plus. Okay, so these were the positively charged ions. Then we have negatively charged ions with a valency of 1, which are chloride, bromide, iodide. Previously it was written iodine, sorry for the mistake. Iodide, hydroxide, nitrate, hydrogen carbonate, hydrogen sulfate. These last ones here are again compounds. OH is hydroxide. One oxygen atom and one hydrogen atom makes hydroxide. Nitrate is NO3. We read this before. Hydrogen carbonate is HCO3. Hydrogen sulfate is HSO4. It is advisable to memorize these symbols of these ions as well. They're only going to help. So these are the negatively charged ions with single negative charges. Then we have the negative charged ions with double negative charges. We write it as 2 and minus. Sulfate, sulfide, carbonate, oxide, sulfide. Here we have the symbols. Then we have the negative charged ions with valency of 3. Goodness, I do a lot of mistakes. It was written 2 minus here, but because the valency is 3, we would write it 3 minus. Previously it was 2 minus, so sorry for the mistake again. Phosphate is the only negatively charged ion with a valency of 3. Okay, so these are the different ions. Memorize this table, it's really going to help. So we are now going to look at this table in which you can see the examples of some chemical formulae. So remember this sign over here, this star sign, indicates that water should be present for these ions to form. The ions the star sign is with. So as you can see, all the acids require water to be present for these to form. So here we have compounds like silver chloride. The ions present in this compound is Ag, is silver and chloride ion, and both of these have single charges. Single positive charge and single negative charge. So as you can see in their names, you will have the positively charged ions name first and the negatively charged ions name second. Silver chloride. You should know at once that silver is the positively charged ion and chloride is the negatively charged ion. Okay, the negatively charged ion names are always in the end of the compound name, and the positively charged ion names are always in the first of the compound names. Sodium hydroxide. Hydroxide again is a negatively charged ion. We read in this table. Okay, should remember this table. And these sodium ion and hydroxide ions form this sodium hydroxide. Because they have single charges, they cancel each other out and they form NaOH, AgCl. Simple, right? But then we have sulfuric acid, whose chemical formula is H2SO4. Now, this is because the ions present in this are a little different. The hydrogen ion has a valency of only 1, whereas the sulfate ion, SO4 is the sulfate ion, you can see it in this table, sulfate SO4, SO3 is sulfite, CO3 is carbonate, O is oxide, S is sulfide. Okay, so the sulfate ion has a charge of -2. So it has a valency of 2, whereas the hydrogen has a valency of 1. And so to balance the charges out for these ions, we would need 2 hydrogen atoms. We would need 2 hydrogen ions and only 1 sulfate ion, because 2 hydrogen ions would make a total charge of +2 and 1 sulfate ion makes a total charge of -2. So then they get balanced, the charges. And that is why the chemical formula in the end is H2SO4, 2 hydrogen ions. SO4, remember, don't confuse this 4 with the number of atoms. This 4 is with the sulfate. 4 oxygen, 1 sulfur atom makes sulfate. There's nothing to be confused of it because it's pretty simple. When we write SO and 4, it means sulfate. There is no such thing as SO only. Then we have hydrochloric acid, which is formed with a hydrogen ion and a chloride ion with single negative and positive charges, so they cancel each other out. There's no rocket science in its equal charges too. So HCl. Nitric acid is also simple, same positive and negative charges, 1 they cancel each other out. But then we get carbonic acid. In this we have hydrogen, which has only a single positive charge, but carbonate has a double negative charge. So it would need 2 hydrogen ions to balance the charges. 1 carbonate and 2 hydrogen ions. So that is why the chemical formula is H2CO3. Before there were HNO3, HCl, no other digits, but here we have H2CO3 because we have 2 hydrogen ions. Okay, we have calcium hydroxide. The ions present again is going to be a little confusing because the calcium ion has a valency of +2 and the hydroxide ion has a valency of -1. So in this case, we would need 2 hydroxide ions to balance the charges because the calcium ion has a charge of 2 positive, but the hydroxide ion has a charge of 1 negative, so they are not equal. So to get them equal, we have 2 hydroxide ions that make the total charge of -2. So the charges get cancelled and in the end the chemical formula is CaOH2 in the end. Again we bracket this OH so that we can see that this OH entirely including the O and the H. So if we just write OH2 with no brackets, it can get a little confusing that maybe we're just saying that the hydrogen atoms are 2 and the oxygen atom is 1 only. So that's going to be a little confusing. So that is why we bracket the OH and write the 2 outside, so that we're talking about the entire hydroxide ion, 2 hydroxide ions, not 2 hydrogen atoms and 1 oxygen atom, okay? So we bracket these out. Then we have ammonium carbonate. Ammonia has a charge of 1 positive, but the carbonate has a charge of 2 negative. So it needs 2 ammonium ions to balance the charges. So that is why we have NH4, 2 CO3. Again, NH4 is bracketed so that we don't confuse this 2 with 4 and it doesn't become 42 or something. So we bracket this out. Then we have iron oxide, iron 3 oxide, because iron is in the form of 2 different ions, iron 2 and iron 3. So that is why we write the number with iron. Some elements have 2 different ions, like iron has 2 different ions, iron 2 and iron 3. So with such elements, we write their valency in brackets in Roman numbers. So iron 3 oxide. This would make it clear that the ions present in this is the iron 3. The valency is 3 plus, not the 2 plus, and the oxide ion is 2 minus. But this is again not simple. Oxygen is 2 minus, but iron is 3 plus, which has a valency of 3, positive 3, and oxide, which has a valency of 2. Now how are these going to get balanced? So you can see that we have 3 oxygen atoms, then we'll have a valency of -6. And so that can get balanced with iron if we have 2 atoms of iron. So 2 atoms of iron would give it a valency of 6 positive, and 3 atoms of oxygen would give it a valency of 6 negative. So iron 2 atoms of 3 plus iron, we get 6 positive. 3 atoms of O, 2 minus atoms, and we will get 6 negative, and then they will get cancel each other out. So that is why their chemical formula is Fe2O3, because there are 2 atoms of iron and 3 atoms of oxygen. So that's right, not all the atoms are in the ratio of 2 and 1 or 1 or 2 or 1 1 or 2 2. Okay, sometimes this also happens. This usually happens in compounds in which one ion has a valency of 3. Another type of compound is the aluminium sulfate, because in this we have aluminium, which also has a valency of 3 positive, but sulfate has a valency of 2 negative. But if we have a compound with an ion of a 3 valency but bonding with an ion of a single valency, then it will be simple. We will just need 3 atoms of the ions with a single valency to balance out with the aluminium or iron ion. But in this case with 2, what we do is that we double up the 3 positive ion so that it becomes 6 positive, so that its valency becomes 6 positive, and then we triple up the 2 negative ion so that its valency is 6 negative. So that is why aluminium sulfate's chemical formula is also Al2SO4 Okay, calcium hydrogen carbonate is simple, but don't take this as if the compound is made up of 3 different ions, okay? It may sound like it because the name is 3-word long, but hydrogen carbonate is a separate ion, HCO3. This is why it is important for you to memorize this entire table so that you get used to these different negatively charged and positively charged ions. So in this we have calcium, which has a valency of 2 positive, and hydrogen carbonate, which has a valency of -1. So it's a single negative charge. So in this again we would need to double up this ion to balance out with this calcium's charge, and we get CaHCO3 2 atoms of HCO3. Again we bracket it out so that it becomes separate. So these were the compounds with their chemical formula and ions. Till now we haven't seen how these chemical formulas are made, okay? We're just reading the already made chemical formulas. Some of the different chemical formulas that we might come across, like sulfuric acid, hydrochloric acid. And also note that all these acids, they always contain hydrogen ions, okay? So in general, we have to remember these points when working out the chemical formula from ions. 1, we have to write down the name of the substance. By substances, we mean the elements, you know. If it's silver chloride, then we are going to write Ag, silver, and Cl, okay? 2, we're going to write down the ions involved. That is, we're going to give them charges. Silver has a single positive charge and chlorine has a single negative charge. Then we balance the positive and negative charges if necessary. Like in silver and chloride's case, it is not necessary. We are not going to do it because they are already equal. But if we have ions like hydrogen and carbonate, then we will need to balance them out. So you know how we balance out. We add one more ion to the positive or negative side depending on their charges. We're going to balance them out, and then in the end we're going to write the chemical formula without any charges. Okay? Because the charges cancel each other out. It's simple. So this is how we are going to work out chemical formulas from ions. Okay? It's very fun to do this, you know. Grab a paper and pencil and let's make some chemical formulas. Like I want to make a chemical formula using this chart here so that it's a little easy. You might forget the ions and their charges. Grab a pencil and paper and let's make some. So to form a chemical formula, we will first need a positively charged ion. We're going to write down a positively charged ion and then write down a negatively charged ion. So I'm going to take sodium as a positively charged ion. So write sodium down, Na. Don't need to write any charge, okay? We're going to write sodium, Na. And let's choose the second ion to complete the formula, chloride. Oh no, we've done this before. Like silver chloride was something like it. We're going to take something a little different. I'm going to take it from a different valency so that we do some balancing stuff as well. I'm going to take carbonate, okay? So this is going to be sodium carbonate. So write carbonate down, CO3. We're not going to write the charges at first. Write the carbonate down, CO3, and we have sodium written down, Na. Now we're going to put the charges, okay? So you should know the charges. That is why I'm telling you to memorize this chart. Sodium has what charge? 1. 1 positive charge. Sodium has 1 positive charge, so we're going to write a plus sign over Na. And the carbonate has a negative charge of 2. So write 2 minus above the CO3. Now your charges are written. Your ions are completely written together. Now what we're going to do is balance out these charges. So you should know whether they are balanced already or not. If the positively charged ion has a charge of 1 positive and the negative charged ion also has a charge of 1 negative, then they're equal. There's no need to balance. But in this case, I've written down sodium and carbonate, which are not equal, whose charges are not equal. Sodium has a charge of 1 positive and carbonate has a charge of 2 negative. So to balance out, we would need 1 more sodium atom to balance out the charges, okay? So 1 more sodium atom would give the charge of the sodium ions a total of 2 positive, which is equal to 2 negative of the carbonate ion. So now that we've balanced out the ions, what we did is that add another atom of sodium. So we now have 2 atoms of sodium and 1 carbonate ion. 2 sodium ions and 1 carbonate ions. Please do not confuse this atoms things that I'm saying. It is sodium ion. I should be saying ions more than atoms, but it's the same thing. Don't think that carbonate is an ion and sodium is not. Sodium itself is also an ion, so is carbonate. And they both are atoms and molecules as well. Anyways, now that we balanced out these things, we're going to write down the end product of both the ions, which is going to be the chemical formula. And so, the chemical formula of sodium carbonate is going to be Na2CO3. In the end, we're not going to write any positive and negative charges. We're going to remove the charges because they're going to get equal. When they get equal, they're going to cancel each other out. So in the end, we write Na2CO3. 2 basically represents the number of atoms of sodium. Na2 when we write Na2, we are basically telling that there are 2 atoms of sodium. But don't confuse this with the carbonate 3 in the end, because 3 represents the oxygen atoms in the carbonate ion. C has no number after it, so it is 1 carbon atom and 3 oxygen atoms. Okay? Na2CO3. That's the chemical formula of sodium carbonate. So isn't this fun, It's fun to form these chemical formulas. Now I explained you how to form these chemical formulas. It is your job to make some more. Enjoy yourself. Here I've given you the entire table of the different positively and negatively charged ions. So just cross them together, make different charges. Iron sulfide, iron carbonate, change the valencies. Don't keep the valencies the same. Change them up. Like take a positive ion from a valency of 1 and a negative ion from a valency of 3 or 2, so that you do some balancing stuff as well. And in the end, the chemical formula is a little complicated, so it's going to get more interesting. Okay? So do this stuff, practice how we can make these chemical formulas. And these are the different compounds which are already made. Like silver chloride, sodium hydroxide, sulphuric acid, hydrochloric acid, nitric acid, all of these are the compounds which are already made along with their chemical formulas. Okay, so it is again advised to memorize this entire table because these compounds are going to come quite often in this chemistry O-level lesson series. Okay, here what we've done is that we've given the ionic compounds, but many compounds are covalent as well, and therefore are not composed of ions, and their chemical formulae must be learned as they cannot be worked out. So right now I've given the ionic compounds. So these ionic compounds can be formed as well, like I told you to form different stuff over here, make different formulas. But the covalent compounds, they are molecules, okay? They are covalent, and in covalent bonding there is no such things as ions, and therefore because they're not composed of ions, they cannot be worked out, and their chemical formulae must be learned. It should be remembered. So let me tell you the chemical formulae of the different covalent molecules. Firstly, we have the molecules of elements: hydrogen, oxygen, chlorine, and nitrogen. And we have fluorine as well. These are the compounds of elements. Basically, these elements are in the form of atoms as well as molecules. So when we say compounds, we mean molecules, okay? So the covalent molecules, I'm talking about the covalent molecules, giving you the formula of covalent molecules. Then first we have hydrogen. The formula of this is H2, okay? We have oxygen, the formula of this is O2, chlorine, Cl2, nitrogen, N2. Now as you can see, in the names of these compounds, we have no idea of any other atom, okay? Like here we have sodium hydroxide. You can differentiate, you can understand that this compound is made up of two ions. One is the sodium and the other is the hydroxide. But in the case of covalent molecules, we have no idea of what ions it is made of. And so that is why we cannot work it out. Like calcium hydroxide, we can work it out, hydroxide and calcium. But in covalent molecules, ammonia, it's completely different. It's not ammonium carbonate, which can be worked out. Ammonia, it cannot be worked out because the name is very different. It is not made up of two different names combined together to form something. It is an actual compound, and the formula of such compounds need to be learned and remembered and memorized. So we have hydrogen, oxygen, chlorine, nitrogen. Their formulas are very simple: H2, O2 for oxygen, Cl2 chlorine, N2 nitrogen. Their symbols and a 2 in the end because there are two atoms of these elements forming the molecules. Then we have water. See, water is such a different name. It's very different, We're not saying aluminium sulfate, iron oxide. We're saying water. Water is basically a name of the compound, H2O. So this name isn't made up of two different names of elements, right? So it cannot be worked out. I hope you're getting my point, okay? That covalent molecules need to be learned. Water's formula is H2O, 2 hydrogen atoms and 1 oxygen atom. Then we have ammonia, whose formula is NH3, 1 nitrogen atom, 3 hydrogen atoms. Then we have carbon monoxide, whose formula is CO. Now, in the compounds I've read before, hydrogen, oxygen, chlorine, nitrogen, water, and ammonia, they are difficult to be worked out. But in the compounds like carbon monoxide, carbon dioxide, it can get a little easy because we're talking about oxide here. Carbon, oxide, by oxide you should remember the oxygen atom. And when we say monooxide, mono means one. So that would mean that it's only one oxygen atom. But when we say dioxide, that di means two. Carbon dioxide means CO2. Carbon monoxide means CO only. Sulfur dioxide would mean SO2. Sulfur trioxide would mean SO3. Tri means 3. Nitrogen dioxide would mean NO2. Hydrogen chloride is different, HCl. But as you can see, they get a little like the ionic compounds. You can guess the atoms from their names. So they're not entirely very difficult. They can be remembered, okay? So carbon monoxide. Think about it. What's going to be the formula of this? CO. That's right, CO. Because we're talking about one carbon atom, carbon monoxide, one oxide ion. Not the ion, I'm sorry. One oxide atom. There's no such things as ions in covalent molecules. So carbon monoxide is CO. Sulfur monoxide, remember that is going to be SO because it's monoxide. Okay, then we have sulfur dioxide, SO2 because there are two oxide. Sulfur trioxide, SO3 because tri means 3. Nitrogen dioxide, and then we have hydrogen chloride. These kind of get quite the same as the ions here. The ionic bonding involves the charges. In covalent bonding, we have no charges. There are some molecules which are completely different, like ammonia, water, nitrogen. These are completely different, okay? These need to be learned. But some of the compounds, like carbon monoxide, they can be worked out. I might have gotten a little too dramatic before. I'm sorry. Carbon monoxide, very simple. One carbon atom and one oxygen atom. So in these, we are basically taking the names from the ions. Like, we're not saying carbon oxygen, we're saying carbon oxide. Sorry, carbon monoxide. Not carbon oxide, we say monoxide. That is why it's different from the ionic compounds. In ionic compounds, we don't say monoxide, we say oxide, like iron oxide, hydroxide, But in covalent molecules, whenever we are going to show only one oxygen atom, we would say monoxide. 2 oxygen atoms, we'd say dioxide. 3 atoms, we'd say trioxide, okay? So I hope you've understood the formulae of covalent molecules and ionic molecules. And you've understood how we can form the formulae as well. So we're going to move ahead on to understanding valency and chemical formulae. So chemical formulae can also be determined by using the valency of atoms or radicals. As I said before, the group number indicates the number of valence electrons. Carbon is in group 6. That is why its valence electrons is 6. But carbon does not bond ionically. It forms covalently only, because the atoms in groups 3, 4, 5 and 6, they bond covalently, not ionically. That is why we have carbon in forms of molecules here in ionic bonding, like carbonate, carbon and oxygen. So carbon is never in the positively charged ion sections or the negatively charged ion section by itself. It is in the form of molecules, because the groups that I just said, 3, 4, 5 and 6, they bond covalently, not ionically. Because losing more or gaining more electrons would cause too much energy, and in these groups we have valence electrons in the middle, somewhere in the middle. They're either more than 2 or less than 7, and so that causes them to not bond ionically but covalently. So covalent bonding is an alternate to ionic bonding for these groups, okay? So the valency is numerically equal to the charge on an ion. Like sodium has 1 extra electron in its outermost shell, because sodium is in group 1 as well in the periodic table. Group number represents the number of valence electrons in the outermost shell. So sodium has 1 extra valence electron in its outermost shell, and so the valency is numerically equal to the charge on an ion. 1 is the valency of sodium, and 1 is the charge of sodium as well. And because sodium has 1 extra electron, it is positively charged. If it had 1 less electron, then it would be negatively charged. Like what I'm saying is that, like the chlorine atom, we say the valency is numerically equal to the charge on an ion, but the chlorine atom has the valence electron 7. It is in the 7th group of the periodic table, so its valence electrons are 7. So what would we say? The valency is 7 of chlorine? No. We would say that the chlorine's valency is -1. Or we would write it just minus. Because it's very difficult for chlorine, for any atom to lose so many electrons, like 7 electrons. And so that is why we write -1 or minus only, so that it is obvious that it needs 1 electron. It needs to gain electrons, not lose electrons. Okay? So valency is basically the combining power of an atom or radical. This is the simplest definition of valency. Now, valencies are always small whole numbers or 0. So the elements which have 0 valency do not form compounds. These are basically the elements which have complete outermost shell, so they do not have any valence electrons. And they do not form compounds. They are inert gases. They all are in the group 8 of the periodic table. Remember, group 8 means 8 valence electrons in the outermost shell, and so 8 is a complete octet. Okay. And so all the gases in the 8th group are inert. They don't react because they have full outermost shells. They don't need to react. They don't need to be stable. They're already so stable. They don't react. Okay. This includes helium. It has a complete doublet, 2 valence electrons. It has a complete doublet. And the other, like radon, neon as well. They all are inert gases. So they do not form compounds. But some elements can have more than 1 valency. And they are said to have variable valencies, and so to distinguish them, a Roman numeral is used. For example, copper 1 to distinguish it from copper 2 ion. Copper has variable valencies. It can be of 1 positive or 2 positive as well. So that is why we write down a Roman numeral after them. Copper 1 would have 1 Roman numeral, copper 2 is written like this, or iron 2 to distinguish it from iron 3 ion. I've told you about this previously as well. Okay? So when working out the chemical formula of a compound, it is necessary to balance out the valency of the atoms or radicals present in the same way that you balanced out the charges on the ions, okay? Valency is not actually the charge. The charge is still something different from valency. But what we're saying is that the valency is numerically equal to the charge on an ion. But the two things are still different, okay? So when we work out the chemical formula of a compound, it is necessary to also balance out the valency of the atoms or radicals present, like we balance out the charges on the ions, okay? So when copper and oxygen atoms combine, there are two possible formulae depending upon the valency of the copper. With copper 2 oxide, both the copper and oxygen atoms have the same valency of 2. Its chemical formula is therefore CuO. But with copper 1 oxide, the oxygen atom needs 2 copper atoms whose valency is 1. And so that in total they would have a valency of 2. So its chemical formula is thus CuO. Sorry for the mistake here again. Just gonna correct it. I seriously do a lot of mistakes in writing. So just like we balance the charges out on ions, we need to balance the valencies as well. So when we have copper 1 oxide or copper 2 oxide, so in general, a simple rule is this. Here we have 2 atoms, okay? X and Y. And here we have the valencies of these 2 atoms. Valency of X and valency of Y. So what happens is that valency of Y moves over to X and the valency of X moves over to Y. So the chemical formula in the end becomes XY, YX, okay? X, Y, X with Y's valency and Y with X valency. XY, YX. And if the valency X is equal to the valency Y, then we write XY, okay? Capital X and capital Y represent the symbols and small x and small y represent the valency, okay? So if the valencies are equal, we only write XY. If they are not equal, we would write down the numbers as well. Like if the valency of X is 1 and if the valency of Y is 2, then we would need 2 X's to balance out the chemical equations. And so we would write X2Y. So the valency also needs to be balanced out, just like we balance out ions. And so this is how we do it. What happens is that when the valency Y moves over to X and the valency X moves over to Y, something happens with their charges as well. You see it over here. Might be a little confusing. Aluminium sulfate, as you can see. So the charge on aluminium is 3 positive and the charge on sulfate is 2 positive. So these are basically the valencies as well, okay? The valencies are equal to the charges, right? So what we do is that bring this 2 of the sulfate over to aluminium and bring this 3 of aluminium over to the sulfate. And then it becomes equal. Because what happened is that the 2, when is multiplied by 3, it becomes 6. And when the 3 is multiplied by 2, it becomes 6 as well. And so XY, YX, they become equal. That is why we write Al2SO4 3. So we can do balance it though. Like we take 2 aluminium ions and 3 sulfate ions, we would get aluminium sulfate, right? We still can balance them out, but this rule can also be used. So go ahead, make some more chemical formulae using this chart, memorize all of this stuff, and do memorize these compounds, the already made compounds, ionic compounds, with their chemical formulas as well. And try to work out these compounds. Like look at the name of the compound and try to understand what ions should be present in this compound and what the chemical formula would be of the compound. Like hide this part of the thing. Hide it with your hand, okay? Don't cheat. Hide it with your hand and write down one of the compound names, like aluminium sulfate. Write it down and now you're going to see the name, aluminium sulfate. Its name is pretty obvious. You can see the ions present in the name. Aluminium and sulfate, right? Aluminium sulfate. So then you just separate out the ions present, write down the charges of each of the ions, and then make the chemical formula by balancing the ions and stuff. Okay? And we use this rule to form chemical formulas. Here I have the Valency table. It's a long table, right? Because it has all the different elements from the periodic table and radicals as well. Now, I forgot to explain you what radicals are. Of course, you might be thinking that hydroxide. This should not have any valency because it's a molecule. It's already complete, like OH. Why does it have a charge on it, even though it's a molecule? A molecule, when it is formed, does not have any charge. It is neutral. But why does hydroxide, sulfate, nitrate, carbonate, hydrogen carbonate, and ammonium, they all have valencies? Basically, this is what radicals are. Radicals, it is also known as a free radical. A radical is an atom, molecule, or ion that has at least one unpaired valence electron. So with some exceptions, these unpaired electrons make valence electron. After it even becomes a molecule, like hydroxide, it's a molecule, OH, right? But it still has one valence electron. Sulfate, SO4, a molecule, a compound, it also has a valency of two unpaired electrons. So radicals are basically atoms, molecules, or ions, anything at all, which still have one or two valence electrons in their outermost shell, unpaired electrons, okay? And they play a very important part in ionic bonding. So these are the different radicals with their symbols and valencies, and here we have the different elements with their symbols and valencies. Remember, do not confuse radicals with negative particles and elements with positive particles, because the radicals are always in the negative side, but there are also other atoms in the negative sides as well, like the chloride ion and the bromide ion and the iodide ion. They're not actually radicals, but they're still negatively charged ions. Oxide as well, sulfide as well, but sulfate, these are free radicals. SO4, it's a molecule. And why is it charged then? Molecules are not usually charged, are they? They're neutral because they're complete. But no, some of the molecules or ions or atoms have at least one or two unpaired electrons. These are some molecules, okay? And we call such molecules radicals. And they're very reactive as well. So, here we have radicals and elements along with their symbols and valencies. Again, memorize all the tables I've given in this chapter, as they are only going to help in the future, okay? So now, we are going to move ahead onto the relative molecular mass. What is this? So we read about the relative atomic mass in the previous chapter, in chapter 4. So in the same way, a compound represented by its chemical formula can also have a relative molecular mass. Okay, this is not the atomic mass, this is molecular mass. Okay, so the relative molecular mass of a substance, this is all written as capital M with a small r, and R in subscript. Okay, so the relative molecular mass of a substance is defined as the average mass of a molecule of the compound, okay, compared with the mass of a carbon atom, which is taken as 12 units. So the average mass of a single molecule of a particular compound is compared with the mass of a carbon atom, is the relative molecular mass of that compound, okay? So molecular mass can also be used for compounds that do not exist as molecules but as ions. And in these cases, the molecular mass is the mass of a formula unit. A formula unit being the simplest statement of the combining ratio of the two or more ions. Thus, the formula unit of sodium chloride is NaCl, which says that there are equal number of sodium and chlorine units in sodium chloride. We then find the relative formula mass of an ionic compound instead of its relative molecular mass. So to find the molecular mass of compounds that do not exist as molecules but as ions, we find the formula mass, okay? Relative formula mass of an ionic compound instead of its relative molecular mass. But now we're going to learn to find out the relative molecular mass of sulfuric acid. I'm taking sulfuric acid as an example here. We can take any other compound, but the way we do this is something like this. Sulfuric acid, H2SO4, contains 2 hydrogen atoms, you can see this in the formula, 1 sulfur atom and 4 oxygen atoms. So the relative atomic masses of hydrogen is 1. Hydrogen's relative atomic mass is 1. You can see this from the periodic table. Relative atomic mass of sulfur is 32 and of oxygen it's 16. So we're going to find the relative molecular mass, like the mass of this entire sulfuric acid molecule. So we know the relative atomic masses of these three elements. So what we're going to do is that we're going to divide their relative atomic mass by their quantities. Like hydrogen, there are 2 hydrogen atoms in this, so we will multiply its relative atomic mass by 2, which is 1 multiplied by 2 is 2, right? And then of sulfur, because it is only 1 atom, we would keep it 32. And oxygen's relative atomic mass is 16, and there are 4 oxygen atoms in H2SO4, so we will multiply 4 by 16, and then we will add all of these together: hydrogen, sulfur, and oxygen. Oxygen is 4 and hydrogen is 2, sulfur is only 1, so it's 32. So when we add all of this, we get 98. So 98 is the relative molecular mass of sulfuric acid. It's pretty simple, right? To find out the molecular mass, we need to memorize the relative atomic masses of each element: hydrogen, sulfur, oxygen, and many other elements, so that we can find it. This was the relative molecular. What we just did is that because we know the relative atomic mass, we multiplied the relative atomic masses of each of the atom by their quantities. Like if hydrogen is 1, so we multiplied it by 2 because there are 2 atoms of hydrogen. Oxygen is 4, we multiplied its relative atomic mass by 4. And then we have sulfur, but it's only 1 atom of sulfur, so we kept it 32. And then we added all of them, we got 98. So 98 is the relative molecular mass of sulfuric acid. Each molecule of sulfuric acid's mass is 98. Okay, now we're going to move ahead and find the relative formula mass of sodium carbonate crystals. Okay, so we're going to consider a common chemical like washing soda, which chemically is hydrated sodium carbonate. This contains 2 sodium atoms, 1 carbon atom, and 3 oxygen atoms, and then 10 water molecules. And each water molecule itself contains 2 hydrogen atoms and 1 oxygen atom. And in total, there are 10 water molecules. So we're going to find the relative atomic masses of all of these. So sodium is 23. The relative atomic mass of sodium is 23. We're going to multiply it by 2 because there are 2 sodium atoms. We get 46. Carbon is only 1 atom. It's 12. Its relative atomic mass is 12, so we're going to keep it 12. Then we have oxygen, which has a 16. The relative atomic mass, we're going to multiply it by 3 because there are 3 atoms of oxygen. We get 48. Then we have water molecules. So first we're going to find the relative atomic mass of 1 water molecule. 2 hydrogen atoms would make 2 relative atomic mass. 2 multiplied by 1 basically, because 1 is the relative atomic mass of hydrogen, and then 16 is the relative atomic mass of oxygen. There is only 1 atom of oxygen, so oxygen plus 2, because 2 multiplied by 1 is 2. 16 plus 2, and then multiply it by 10. Multiply the amount by 10, and in the end we get 180. Okay, then we add all of these together, all of their atomic masses together, and we get 286. Okay, so finding the relative formula mass is the same as finding the relative molecular mass, as you can see, except for that, because sodium carbonate crystals is an ionic compound, so we found the relative formula mass of this. Before, we found the relative molecular mass of sulfuric acid, because sulfuric acid, it is a molecule. So in simple words, the formula mass and the molecular mass is almost the same. It is the same actually. I mean, haven't you seen when we took it out, right? So if we say to find the relative formula mass, you should know that it means the same thing as finding the relative molecular mass. So all we do to obtain relative molecular or formula masses, we add together the individual relative atomic masses, and these can be found from the periodic table. We find relative atomic mass of each atom in a compound, multiply it with the number of atoms of that element it has in the compound, and then add all of the masses together. In the end, we are left with the relative molecular mass or formula mass. So now that we've understood how to find the relative formula or molecular mass, we're going to move ahead on to understanding the percentage composition. The percentage composition of elements in a molecule. So if we know the chemical formula of a substance, we can calculate its percentage composition by mass without doing any experiment. So the rules are, number 1, we're going to write down the chemical formula of the substance. Like H2SO4 is a chemical formula, we write it down, okay? Number 2, we find out its relative molecular mass. We just did previously, that is how we're going to do it. Number 3, we're going to express the total mass of each element as a percentage of the total relative molecular mass. And the sum of all the percentages must be 100. Now we're going to learn to do this. Okay? So, the first steps are pretty easy, right? But the third step is something we need to learn to do, okay? So, firstly, the percentage of a pure substance never changes. For example, a water molecule is a compound composed of 2 elements, hydrogen and oxygen. And such a molecule will always contain 11.11% hydrogen and 88.89% oxygen. And if in any way this percentage changes, it will not remain the water molecule. Or I would say it will remain the water molecule, but it would not be pure then. The percentage composition doesn't vary, okay? This percentage composition, this 11.11 and 88.89 oxygen, is equally true if we take our sample of water from New York, New Delhi, or New Zealand. So even the small quantities of water moisture found on the moon have the same percentage composition. The chemical composition of a compound is fixed and never varies. We read this in the chapter of compounds, mixtures, and elements, Elements, compounds, and mixture, In that chapter, we differentiated between mixtures and compounds, and we read that a mixture's composition can vary, whereas a compound's composition does not vary. It is always fixed. If it does vary, then the compound is not pure. Okay? So, now let's learn to find out the percentage composition of sulfuric acid. We saw over here what we're going to do. So, the 3 steps here. We're going to apply these steps on finding sulfuric acid's percentage composition. Number 1, we are going to write down the chemical formula of the substance, H2SO4. Number 2, we will have to find out its relative molecular mass, which we have done previously by the method I showed before, and it is 98. Number 3, we're going to express the total mass of each element as a percentage of the total relative molecular mass, and the sum of all the percentages must be 100. So of these 98 mass units, 2 units are due to the hydrogen atoms, right? 32 units are due to the sulfur atom, and 64 units are due to the 4 oxygen atoms. Okay? I'm basically saying the masses of the 3 elements. The mass of the entire molecule is 98, but 2 units are of the hydrogen atom because there are 2. Relative atomic mass is 1, we multiply by 2, we get 2. 32 units are due to the sulfur atom. 32 is the relative atomic mass of sulfur, and it is only 1 atom, so we keep it 32. And 64 is due to the 4 oxygen atoms. 16 is the relative atomic mass of oxygen, and when we multiply by 4, because there are 4 oxygen atoms, we get 64. So of these 98 mass units, 2, 32, and 64 are due to these specific atoms. Therefore, the percentage of hydrogen, the percentage of sulfur, and the percentage of oxygen are found like this, starting with hydrogen. What we do is that we divide the hydrogen's atomic mass, that's right, with 98, which is the relative molecular mass of the entire molecule. We divide it and then multiply it by 100 to find the percentage. We get 2.04%. And to find the percentage of sulfur, we would divide 32. 32 is the relative atomic mass in this atom. The relative atomic mass of hydrogen is 1, but in this atom it is 2. So that's what we do. We divide 32 by 98 and multiply by 100, we get 32.65. And then of oxygen we divide 64 because the relative atomic mass of oxygen itself is 16, but in this atom it is 64 because there are 4 oxygen atoms. So we divide 64 by 98 and multiply by 100 and we get 65.31%. Okay, now we're going to use this calculator to find if all of these percentage add up to 100. First with 2.04. We add 32.65 and then add 65.31. We hit enter and we get 100, a perfect 100 actually. So this is how we find the percentage composition of sulfuric acid. Now I want you guys to find the percentage composition of sodium carbonate crystals. Bring a pen and paper and write down this. Number 1, chemical formula. Number 2, relative molecular mass. And this stuff in the end. So first you need to know the chemical formula of sodium carbonate crystals. Now I've given you the previous so many tables. You need to go back there and find the sodium carbonate crystals formula. So first we're going to write down the chemical formula of sodium carbonate crystals, which is, let's do it right now. I'm going to tell you, okay, fine. But you're going to do it with me, okay? Okay, I know this is a very terrible handwriting, but this is the chemical formula of sodium carbonate crystals. Na2CO3 10H2O. Okay? Remember, whenever we're talking about crystals, there is water in it. So this is the chemical formula of sodium carbonate crystals. And now that I've already taught you how to find the relative molecular mass of a compound, you're going to do this part at least yourself, okay? I've given you the chemical formula of sodium carbonate crystals. You can even find it on Google. Just search it up, sodium carbonate crystal formula, and you'll get it. But I've given this to you right now. Now you find the relative molecular mass yourself. Don't Google it. Don't do any of that. Do it yourself. Pause this video and do it. Okay, now in the end, no matter how much I say, I do have to write it down myself as well. So the relative molecular mass of sodium carbonate crystals is 286. Again, terrible handwriting, I know. Let me just make it a little better. Yeah, now that's much cleaner and better, right? So chemical formula is Na2CO3.10H2O. Okay. Then we have the relative molecular mass, which is 286. Okay. Now, of these dash mass units, I just didn't write it over here because I was thinking, I assume you're going to find it yourself. So of these 286 mass units, dash units are due to the dash atoms, dash units are due to the dash atoms, and dash units are due to the dash atoms. Okay, sorry for this. Dash units are due to the sodium atoms, okay? Now you're going to write down how many new units are due to the sodium atoms, and then you're going to write down how many units are due to the carbon atoms and how many units are due to the oxygen atoms. And in the end, you're also going to write how many units are due to the water molecules, okay? Pause this video and do it. So, I'm going to write it down for you. Here we are again with some colorful stuff now. So of these 286 mass units, 46 units are due to the sodium atoms, okay? Correct yourself if you're wrong at the moment. 46 units are due to the sodium atoms, 12 units are due to the carbon atoms, 48 units are due to the oxygen atoms, and 180 units are due to the water molecules, okay? When we add all these units together, we get 286. Do it right now and you'll get it. So therefore, the percentage of sodium, percentage of carbon, so percentage of oxygen, and percentage of water as well. I just showed 3 over here, you're going to do it 4, okay? At relative atomic mass of the unit is divided by the molecular mass and then multiplied by 100. This is what you do with all of the atoms. And I want you to do it yourself right now. Find out the percentage of all of these units of sodium carbonate crystals. And so what we get is something like this. The percentage of sodium is equal to 46 divided by 286. 46 is the unit of sodium, and we multiply divided by the molecular mass, and then multiply by 100, we get 16.08%. For carbon, we have 12 divided by 286 multiplied by 100 and 4.20%. Oxygen, we have 48 divided by 286 multiplied by 100 and we get 16.78%. And of water, lastly, we have 180 divided by 286 multiplied by 100 and we get 62.94%. So, we just found the percentage composition of sodium carbonate crystals. Wasn't that fun? We got a little bit of maths in here, and all you need to do to remember this is memorize it again and again. So now that we've understood how we can find the percentage composition of a compound, we've practiced it as well. I hope you've actually practiced with me, like I said, to find the chemical formula first, then the relative molecular mass. I hope you did this yourself to 86. Don't just skip to the next. That is the only way you would be able to practice and understand nicely. The moment you do it yourself, you get to understand it. Okay? So, these were the 3 different stages of finding percentage compositions. Now we're going to move ahead on to calculating the mass of an element in a compound. So, if we know the percentage of an element in a compound, then it is easy to calculate the mass of that element. So, the mass of an element is equal to the percentage of the element and multiplied by the mass of the sample, which is equal to atomic mass of the atoms of the element in the formula divided by the molecular mass of the compound. This is how we find the percentage of an element, right? We saw right now. And then multiplied by the mass of sample. It means the same thing, just clarify the percentage part a little more. So, doing this, multiplying mass of sample with percentage of element, we can find the mass of the element. So, let's see what we mean by this, okay? We are given an example over here. We are told to calculate the mass of sodium in 10 grams of sodium carbonate crystals. Okay? So, previously we weren't given any amount of sodium carbonate. We were just given sodium carbonate. It's pretty simple, right? But now we have to find the mass of sodium in 10 grams of sodium carbonate crystals. In a particular volume of this compound, we have to find the mass of sodium. So how do we do this? You might be like, oh my god, this is going to be really, really complicated or really tricky or something that's really difficult. I used to think the same way when I was learning. But now I think that it's just a piece of cake once you memorize this stuff. So, what do we do first? First of all, you need to take out all of the atomic masses of all of the elements in sodium carbonate crystals. The atomic mass of sodium is 23, the atomic mass of carbon is 12, the atomic mass of oxygen is 16, and the atomic mass of hydrogen is 1. Sorry for the little j, that was supposed to be a bracket over there, okay? Just corrected it over here. So these are all the atoms, the different elements in sodium carbonate crystals, okay? Now, the atomic mass of atoms of sodium in the formula Na2CO3 dot 10H2O. This is the entire formula of sodium carbonate crystals, right? Now we're going to find the atomic mass of sodium, okay? Of atoms of sodium actually in this formula. So the atomic mass of sodium is 23. We multiply by 2 because 2 is the number of atoms. There are 2 atoms of sodium in this formula, in this compound, right here. So we multiply 2 by 23 and we get 46. So the atomic mass of the atoms of sodium in this formula is 46, right? Now, the molecular mass of the compound is equal to 286. We found it previously. So, the mass of sodium in 10 grams of sodium carbonate crystals would be equal to 46 divided by 286, okay? 46 is the atomic mass of the atoms of sodium in this, and we divide it by the molecular mass of this compound, and then we multiply it by 10, the amount of grams of the compound they've given. Right now they're 10. If there are 5, then you add 5, then we multiply it by 5, 3 or anything else, right? So we multiply by 10 and we get 1.61 grams. So this was it. This is how simple it is to find the sodium in 10 grams of sodium carbonate crystals. What we did previously was when we found the percentage, we divided the atomic mass of the atoms of the different element in sodium carbonate crystals with the molecular mass of the sodium carbonate crystal, and then we multiplied it by 100. But so that was the percentage composition. In this, all you have to do is that instead of we do the same thing, find the atomic mass of the atoms of whatever you want to find out, like sodium in this case, how much atomic mass there is of sodium in the formula, okay? Not just the atomic mass. We multiply by 2 because that is the number of atoms. So in the formula we have 46, and then we divide it by the molecular mass of the compound, and then instead of multiplying by 100, we multiply it by the amount of sodium carbonate crystals they've given us. And that could be any amount. But in this case, it is 10. We multiply it by 10, and in the end we get 1.61 grams. So 1.61 grams is the mass of sodium in 10 grams of sodium carbonate crystals. Okay? I hope you've got it. So this is how we do it. Calculating the mass of an element in a compound. So now I want you to calculate the mass of water in 10 grams of sodium carbonate crystals. Grab a pen and paper, write this down. Write down example as a heading, and then write calculate the mass like it's written over here. Example, and then write down calculate the mass of, not sodium, water in 10 grams of sodium carbonate crystals. Okay, I'm keeping it simple so that it's not very difficult for you. I'm not giving any other compound right now. And then you have to write all this stuff. Write down the atomic masses of all of the different elements in sodium carbonate crystals. So now I'm leaving it up to you to calculate the mass of water. Okay? So pause this video and do it yourself. And if you can't understand it, rewatch this entire section in which I'm calculating the mass of sodium in 10 grams of sodium carbonate, and you have to just replace sodium with water. I hope you've done it right now, and if you have, let me tell you how we can find the mass of water in 10 grams of sodium carbonate crystals in detail. Again, we find out the atomic masses of all of these here, write them down. Remember, whenever we see a compound and we have to calculate the mass of whatever in it, the first thing you need to do is remember all the atomic masses of the different elements that are given in the compound, okay? The moment you do it, write down all of these atomic masses, because in this sodium carbonate crystal we have sodium, carbon, oxygen and hydrogen, because there is H2O in it too. Write down all of their atomic masses, first of all. Now that we've done this, it will be easier for us to access these atomic masses. So, to find out the molecular mass of water in 10 grams of sodium carbonate crystals, we do something like this. We find out the molecular mass of all the water in the formula Na2CO3 10H2O. And so, the atomic mass of water is 18. We multiply by 10 because there are 10 water molecules in this formula, and we get 180. Molecular mass of the compound Na2CO3 10H2O is 286. Simple, what we do is that we divide 180 by 286 and then multiply by 10, the given amount of sodium carbonate crystals, and we get 6.29 grams. Okay? Again, it's the same thing, but it's so simple as you can see. It is almost the same as finding the percentage composition, except for that in the end we don't multiply by 100, we multiply it by the amount of compound given. So now I hope you've understood what we mean by calculating the mass of an element in a compound. The mass of a specific element in a specific amount of compound, okay? This heading might be a little confusing because you can find the mass of an element in a compound, but what we're saying is we have to find the mass of an element in a particular amount of a compound. Okay, like 10 grams of sodium carbonate crystals, 10 grams of sodium chloride, or any other compound, or 5 grams of sodium. How much sodium is in 4 grams of sodium carbonate crystals? Okay, so this is what we mean by this. So, I hope you've understood this. I hope you've practiced as well. You might get a little confused in the beginning You might have some wrong answers at first, but don't worry about it. The more you practice, the better you get at it. The moment you understand it completely, it will be a piece of cake. So now, we are going to move ahead to understanding the empirical formula. Okay, so the empirical formula is basically the formula from the percentage composition. Okay, here we have the definition of this. The empirical formula of a chemical compound is the simplest formula which shows the relative numbers of the atoms of the different elements present. So, it is basically a formula of a chemical compound which basically shows the simplest formula with the relative numbers of the atoms of the different elements present, okay? Like with the smallest numbers present, as if we're telling a ratio or something, you know? So, empirical formulae can be determined once the percentage or mass of each element is known. Remember, the percentage or mass of each element is known. The rules are, number 1, we have to divide the percentage or mass of each element by its relative atomic mass. Number 2, we have to divide by the smallest number to convert to the simplest ratio. And number 3, the number of atoms of the different elements is the empirical formula. So, without going into more detail of explaining how this is done, let's just see how it is actually done and what we get in the end. So, given that a molecule contains 88.89% oxygen and 11.11% hydrogen, what will be its empirical formula? So, right now we're talking about the water molecule, okay? And this is made up of H2O. And so, what is going to be its empirical formula? First, we have to divide the percentage by atomic mass. This is what we see here. Number 1, we have to divide the percentage or mass of each element by its relative atomic mass. So, we are going to divide the percentage by atomic mass. Hydrogen's atomic mass is 1 and oxygen's atomic mass is 16. And the percentage of hydrogen in this water molecule is 11.11 and of oxygen it is 88.89. We divide it and we get these two things. For hydrogen we get 11.11 and for oxygen we get 5.55. Now, they're telling us the second point is that we have to divide by the smallest number to convert to the simplest ratio. And so, what we get here is 11.11 and 5.55. So the smallest in these is the 5.55. So what we do is that we divide this 11.11 by the 5.55 and for hydrogen we get 2. Then we divide the 5.55 by the 5.55 and for oxygen we get 1. And so this is the empirical formula. 2 and 1. H2O is 1. Okay, so the empirical formula in this case is the same as the chemical formula. It is water. However, the molecules like H4O2, H6O3 or H8O4 would also have the same percentage composition and therefore the same empirical formula. So it is important not to confuse empirical formula with the molecular or chemical formula. What determines this is the relative molecular mass of the compound, okay? For water, this is 18. So its molecular formula is H2O. If water's relative molecular mass were 36, then its molecular formula would be H2O4. So remember, empirical formula might be equal to the molecular or chemical formula, but they both mean different things, okay? Molecular formulas tell you how many atoms of each element are in a compound, but empirical formulas tell you the simplest or most reduced ratio of elements in a compound, okay? So empirical formulas tell you the simplest ratio of a molecule or a compound, okay? As what we read in the beginning, the empirical formula of a chemical compound is the simplest formula which shows the relative numbers of the atoms of the different elements present. It's like a ratio. Like for H2O, this is the ratio H2O, right? We find the ratio like this. We divide the percentage of the element by its atomic mass for all of the atoms, okay? Like it's not the case for water only. Like if we want to find the empirical formula of H2SO4, we have lots of other elements there. And so we would need to take out we will need to divide all of their percentages by their atomic masses as well. Their percentage in the H2SO4, okay? Hydrogen's percentage in water is 11.11, but in other things, the percentage of different elements would be different than this, okay? And so we would take out the percentage of how many elements are there in H2SO4. Sulphuric acid, we have hydrogen, sulfur, oxygen, and water, right? And water gets broken down into the stuff as well. So in the end, it is hydrogen, sulfur, and oxygen. So we divide all of their percentages by their atomic masses. You have found the percentages of these as well, haven't you, before? Over here when we were learning about the percentage composition of sulfuric acid. Here we have the percentages of all of these. Hydrogen's percentage is 2.04, sulfur is 32.65, and of oxygen is 65.31. So what we do is that we divide each of their percentages by their atomic masses. Like for hydrogen, 2.04 would be divided by 1. Sulfur's 32.65 would be divided by 32 because that's sulfur's atomic mass. Oxygen's 65.31 would be divided by 16. And so the element which would have the smallest number, like in the water case, we have oxygen. It has the smallest answer, like 5.5. Hydrogen had a bigger answer, 11.11. So we need an element which comes up with the smallest number, the smallest of all of the elements. And so then we would divide all of the elements answer to this division. We're going to divide it with that smallest number, okay? And including that number itself, we're going to divide that number with it as well. And in the end, we would get the simplest ratio. So you know what? Let's just do it right now. I want you to grab a pen and paper and divide these percentages with their atomic masses. Okay? So here I've written down all of their answers. Hydrogen is going to be 2.04 again because it's the same. We're going to divide by 1. Sulfur has 1.02 and oxygen has 4.08. So as you can see, the smallest number here is the sulfur's answer here, 1.02. So what we're going to do is that divide all of the other numbers, 2.04 and 4.08, by this 1.02. We're going to divide 1.02 as well with it. And so this is what we get. I divided hydrogen, this percentage was 1.02 and I got 2. I divide 4.08 with 1.02 and I got 4. As you can see, they're like whole complete numbers. And when I divide 1.02 by 1.02, I got 1. So this is the simplest ratio of H2SO4. And as you can see, it is the same as the chemical formula, 2, 1, 4. 2 is hydrogen, 1 is sulfur, 4 are oxygen. But it is different than it. Every empirical formula would be equal to the chemical formula, but it means a different thing. An empirical formula is basically the ratio, the simplest ratio of atoms in a particular compound or molecule. Okay? So I hope you've got the point. I've also found the chemical formula, I've also found the empirical formula of H2SO4 in the same way you can find the empirical formula of other stuff. The thing that you have to remember is that this is how we find the empirical formula. Number 1, we divide the percentage or mass of each element by its relative atomic mass. Number 2, we divide by the smallest. Okay, we can also divide the mass of each element by its relative atomic mass. Number 2, we divide by the smallest number to convert to the simplest ratio. And number 3, the number of atoms of the different elements that we get is the empirical formula that we get in the end after dividing by smallest numbers. Okay? So I hope you've understood this. It was pretty simple. Every empirical formula is equal to the chemical formula as well. And empirical formulas can be determined by experiment as well. For example, magnesium combines with oxygen to form magnesium oxide. Anyways, now that we've understood this, we are going to move ahead onto chemical equations. Okay, now, a chemical equation is a useful way to summarize what has happened in a chemical reaction. and it can be written in words, but it is usually more convenient and certainly quicker to use chemical formulae, which are themselves a chemical shorthand. So again, a chemical equation is a useful way to summarize what has happened in a chemical reaction. So we're going to learn to write chemical equations now. So firstly, what you start with in a chemical reaction are called reactants, the reactants. You can tell by the name that these are supposed to react, okay? And these reactants are written on the left-hand side of the equation. So these are something that come first. Of course, two things react to form a product. They would be the first ones, right? So we write reactants first on the left-hand side, and then what we end up with after the chemical reaction are called the products. And these are written on the right-hand side of the equation. Pretty obvious. So, when writing chemical equations, to start with, it is advisable to follow these steps. So number one, what you want to do is that we have to write down the equation in words, using either the information given or your own chemical knowledge. Okay, so right now I'm saying that I am going to, like, magnesium plus oxygen makes magnesium oxide. That is going to be our example right now. So the first thing you have to do is that write down the equation in words like this. Magnesium plus oxygen with an arrow means that there's a change in this, there's a reaction. This means there's a reaction and it becomes magnesium oxide. And so these here are the reactants, as you can see, and this here is the product, like we read before here. Okay, so this is the first step you want to do. Write down the equation in words, okay, with the information you have been given. It's like it's written down that you have to make an equation of this thing, what is going to be the product of these two reactants. Then you have to do it like this. The next step is to then write down the correct chemical formula for every reactant on the left hand side of the equation and every product on the right hand side. Okay, so before we had written them in words. Now what is the magnesium symbol? Yeah, Mg, of course. Oxygen, O2. Yes, we use a molecular form of oxygen over here. And the product becomes MgO. So the chemical formula of a magnesium oxide must be MgO, as the magnesium ion requires only one oxide ion to balance it. Okay? Because the magnesium has a charge of 2 positive and the oxide ion has a charge of 2 negative. Okay? Then what we have to do is that we have to, the third step is to balance the equation. And this involves making sure that the number of atoms of each element before and after the reaction is the same. If this is not true, then the law of conservation of mass has been ignored, which is obviously not allowable, okay? So balancing equations is sometimes a little difficult, but it must be remembered that only the proportions of the reactants and products may be changed, not their chemical formulae, okay? So previously we had something like this. Now as you can see, we have O2, right? This equation is certainly not balanced because we have O2 over here, and in the product we have only one oxygen molecule. In the beginning there is 2 oxygen molecules, of course, 2 oxygen atoms, right? So to balance it out, what we do is that we have 2 magnesium ions. We make magnesium have 2 ions because then the 2 get cancelled. Then we have a balanced equation. MgO, then we have 2 MgO molecules. This balancing ensures that we have 2 magnesium atoms and 2 oxygen atoms on both sides of the equation. Before we had 2 oxygen atoms and 1 magnesium atom on the reactant side, and on the product side we had only 1 magnesium and 1 oxygen. So this was not at all balanced. So then what we did is that made magnesium 2, so now they are 2, right? And MgO can only be like 1 magnesium and 1 oxygen. So when we made the magnesium have 2 ions, we now have 2 magnesium oxide molecules. Okay? Then the fourth step is to finally put state symbols in the equation for every reactant and product. So solid is represented as with a small s. You have to do it in brackets, okay? Liquid is represented as a small l in bracket, and a gas is represented as a small g in the bracket. And aqueous means dissolved in water. That is represented as AQ in a bracket, okay? So now you have to put the state symbols. So magnesium oxide is a white smoke consisting of fine white solid particles. So magnesium oxide is definitely solid, okay? As I said, it's solid particles, right? O2 is a gas, oxygen. You should know this, of course. Magnesium is a solid as well. So these are the 4 steps of writing a chemical equation, right? It was very simple and very fun as well. First step is to write it in words. Then we write them down with their correct chemical formula for every reactant and product. Then we balance the equation, and in the end we put the state symbols. So this is a complete chemical equation for the burning of magnesium in air. Now I want you to make a chemical equation yourself. I want you to make a chemical equation for the reaction between marble chips and hydrochloric acid, okay? So grab a pen and paper and go ahead. Marble chips are chemically calcium carbonate, okay? And this reacts with an acid, which is hydrochloric acid, to form a salt. It forms water and carbon dioxide. So it forms salt, water, and carbon dioxide. Okay, so write this down. The reactant side is going to be calcium carbonate plus hydrochloric acid. In the middle there is supposed to be an arrow, and then you're going to write it in words first, like we said in the beginning. The first step is to write it down in words. And the product side, we're going to write calcium chloride, that is the salt, okay? Water and carbon dioxide. As I said, marble chips react with an acid to form a salt, water, and carbon dioxide. So calcium carbonate plus hydrochloric acid makes calcium chloride, water, and carbon dioxide. Okay, now I want you to construct a chemical equation for this. You have to find out the chemical formulas of each of these. The second step is to write down the chemical formulas of each of the products and the reactants. And then you want to balance the entire equation, and in the end put state symbols in it. Okay, so do this, practice on your own. Pause this video and practice making this chemical equation. I'm not going to tell you the answer yet, so I'm going to wait for you. Now I hope you've made this equation. Of course you needed to stop the video for it. And so the equation in the end that you get is CaCO3 with S in the bracket, which means that it is solid. CaCO3 is solid. You have put the state symbols. Plus 2HCl. With the bracket there has to be an aqueous, because HCl is dissolved in water. Every acid is. Okay? It is aqueous. And the product side we write CaCl2 aqueous plus H2O liquid plus CO2 gas. Okay? So notice that acids are always in aqueous solution and that calcium chloride is soluble in water. Calcium chloride is aqueous. Okay? We write calcium chloride aqueous because it is soluble in water. Whereas acids are always in aqueous solution, they're always dissolved in water, okay? So there's a difference between both. But we would write aqueous on both their sides, okay? CaCO3 solid plus 2HCl aqueous form CaCl2 aqueous plus H2O liquid plus CO2 gas. So I hope you have the same equation as I'm saying it. So this is how we make chemical equations. I hope you've understood. It's very simple, as you can see. Reactants and products, and a very fun thing to do. You can practice it even more, make different stuff, and then balance the equation. So the more you practice, the better you're going to get at it. Now I'm going to move ahead to the last topic of this chapter. I know there have been lots of topics in this chapter. We've learned to make so many things. You've learned to find the molecular mass and lots of stuff like percentage, composition. It has been quite fun, hasn't it? In this chapter we have done quite a lot of maths, like simple maths. And you need to memorize all these equations. And you need to memorize all of the equations given in this chapter, so that whenever you're asked to do something like find out the percentage composition or find out how much sodium is in 5 grams of sodium carbonate, you would be able to do it. The more you memorize it, the better you remember it, okay? So, now we're going to move ahead on to our final topic of this chapter, Ionic Equations. Now this is very simple. We just saw chemical equations right now, but Ionic equations are something different. So far we have been writing full chemical equations to represent chemical reactions, like this, We're going to write 2Mg plus O2, like everything. We're writing down every single thing, full chemical equations. However, if the equation involves the coming together of ions in solution, then it is quicker to write the Ionic equation. Okay, we're not talking about the covalent stuff. We're talking about when ions come together. Ions form Ionic compounds. So whenever the equation involves the coming together of ions in the solution, then it is quicker to write the Ionic equation. So consider the case where we add an alkali like sodium hydroxide solution to copper 2 sulfate solution. The full balanced equation in words and formulae would be something like this. I have written it down in words and in formulae as well. So sodium hydroxide plus copper 2 sulfate form copper 2 hydroxide plus sodium sulfate. They kind of like got crossed, haven't they? Like sodium hydroxide, copper sulfate, sodium became sulfate, copper became hydroxide. Anyways, in chemical formulae we write it like this. We have to write their chemical formulas, each of their, and then we balance the entire equation, making sodium 2, and then we do this, and in the end something like this, okay? So this is the full equation. But if all the ions are written out fully, we get something like this. Now, you can see that the sodium and sulfate ions, these sulfate ions, are common to both sides of the equation. So this means that they have been present throughout and remain unchanged. So because of this, they are called spectator ions. Okay? So what happened is that we have sodium hydroxide, NaOH, and copper sulfate. And then afterwards we get copper hydroxide and sodium sulfate. So sodium sulfate get together in the end, and in the beginning they're also there. So they have been present throughout this equation and remain unchanged. Okay? And so because of this, they're called spectator ions. And it is simpler when writing Ionic equations to leave out spectator ions. So we cut down all these sodium and sulfate ions, we remove them, and the Ionic equation for the reaction then becomes simply this. Copper plus hydroxide is copper hydroxide. Because sodium and sulfate were present in the beginning and in the end, and they remain unchanged. Okay, so this is what Ionic equation is. In the Ionic equation, we just leave out the spectator ions, those ions which are present and they don't change in the end. So they're just extra ions, They're not really involved in the equation any much. So that is why we cut down the equation into something simpler. Whereas the equation actually is a full equation in which there's like loads of other stuff. Okay. Now, Ionic equations are useful to represent certain types of reactions. For example, oxidation and reduction reactions, neutralization reactions, ionic precipitation reactions, displacement of halogens, and in the displacement of metals. And we are certainly going to look at all of these reactions afterwards in other chapters. It's going to be really fun too. So don't think that these reactions are ending in this chapter. There's still a lot more equations that we have to go through. So this was it for Ionic equations. As you can see, all of these in the end, they all contain ions, all of these reactions, oxidation and reduction. Like it's ionic stuff going on here. That is why Ionic equations are used. They are only used in the equations that involve the coming together of ions. Okay? That is why they're called Ionic equations. So this was it for today's chapter. Chemical formulae and equations. We have successfully completed all these learning objectives. As you can see, we've learned to state the chemical symbols of some common elements. That was the first thing we did here. Understood the chemical symbols. Then we learned to deduce the formulae of simple compounds from the relative numbers of atoms present and vice versa. We learned to define the relative molecular mass of a compound. We learned to deduce the formulae of ionic compounds from the charges on ions or the valency. Not only learned to define the molecular mass, but also learned to calculate the molecular mass of different compounds. Then we learned to calculate the percentage composition of an element in a compound when given appropriate information. And we learned to calculate the empirical formula and molecular formulae from relevant data. In the end, we understood how we can construct balanced chemical equations with state symbols and construct ionic equations with their state symbols. So this was it for today's chapter. I hope you've understood everything and had a lot of fun in this, because there was a lot of equations and stuff and a lot of things to remember. So memorize, practice, and you're going to get better at it. The next chapter is going to be about the mole. So thanks for watching, and I'll see you in the next video.